This is Paul from Force Attack. In this lecture, we are going to deal with the improper integrals. There are two types. The first type is infinite interval. I'll give you the definition here. We have three cases. Look at the first case. If we have the function here is continuous goes to infinity. Okay, so for when x goes to the function will not goes to infinity definitely. Okay, so the domain is x goes to infinity. From a to infinity, can we look at what is the area under the curve between a to infinity? Okay, we say it's not a stop. So because infinity is not a number, right? Infinity is not a number, so we cannot directly to define the area use a definite integral. This is not a definite integral, right? It's from a to not a fixed number. This we call the improper integral. But we know is there is a kind of area under the curve. How to define? We define it this way. So give you variable t is at here, of course greater than a. We find the area from a to t, and then we move t. See, we move t toward approaching infinity. You can imagine. So this area will approach to the area under the curve, right? So that's the definition. I mean, we find a t first and then take a limit. We get this idea. And the second case, if the lower case, the first case is the upper bound, the upper limit is infinity, right? The second case, the lower limit is negative infinity. Means we're going to get the area under the curve from negative infinity to b. So how to define? Still the similar idea. Give you t and then find this area and then let t goes to left approach negative infinity. So it's the definition here. Find the area. This is definitely is definite integral, right? From t to b. This is the area I highlight. And then let t approach negative goes to negative infinity. Here is the one. The last one. Have a look at it. If the domain this time is from negative infinity to positive infinity. So look at it, what the area under the curve. Okay, we do this way. From anywhere you cut, like at the point C. So we cut into two parts of the area. Look at the left part is the second case. The left part is the second case. The right part is the first case. I means negative infinity to integral we can define as one improper plus another improper. Okay, so both the improper we already defined it. Of course, someone probably will ask, if the limit does not exist, how do you say? Yes, do. We do give a concept. See, the improper, no matter is this or this, okay, the integrals are called convergent if the limit exists. If the limit exists, we said that the improper integral is convergent or the integral converges. The second, if the limit does not exist, we say what? We say the improper integral diverges or is divergent. So we get the definition. So how about the third case? We need both divergent. We need both improper divergent. Then we can define the third case is divergent. Any one of these two is divergent, and the third case is divergent. We get the idea. Okay, so now I give you one example. Can we look at how to do these questions? We have an integral. Okay, so the integral is there. Can we see? Okay, the integral is what? It's improper, right? Because it's not from fixed number to fixed number. Now this is the integral. So what do we need to do? First we know, see, this belongs to this type of infinite interval, right? The interval, we say the interval is goes to infinity. So how do you do this? We have to use the definition, right? What is the definition? Okay, so I get here. Have a look at. So I put this one to here, and then I do the calculation. use the limit definition. Do you remember what the limit? This is the first case, right? We need to set up t here, and then that the t goes to infinity. So I set up t here, and then of course no change for this integrand. No change this. I mean we find a small part, and then what to do? Let t approach infinity. This is the definition, right? This is exactly the definition. Okay, so this is important, everyone. So when you do this improper, you have to show the definition. Otherwise, no one understand what that is mean. Okay, this is the definition. Now this is easy. What are we going to do? Find this, right? And then take a limit. 2 steps. The first step is to define the integral. Okay, everyone know this is a rational, right? This is a rational. What do we need to do now? I'll put it here first. Can we look at what is the integrand this time? It's rational. Okay, the integrand is 1 over x squared plus x. You can find the fact. You have to find the factor first, right? If I find the factor, easy. 1 is 1 factor, another is x plus 1. Okay, I mean this is a rational function or integral. We need to find the partial fraction. You can directly use the theorem to find the partial fraction. However, this is an easy case. So everyone, so look at this. We have an easy case to directly find the partial function. We can manipulate the 1. 1 equals x plus 1 minus x. Okay, and if we do this way, see, we can separate into 2 factors. Okay, each factor is one partial fraction. The first one is 1 out of x. The second one, we cancel this x, is 1 out of x plus 1. Can you see this? This partial fraction is easy, right? This is very easy to find the partial fractions. Okay, if you find the partial fraction, now what do we need to do? Plug this in. We think, right, we need to get the answer directly. T approach infinity from 1 to t. I'll copy this first. Put it here is 1 out of x minus 1 plus 1, x plus 1 dx. And then someone, you also can use the partial fraction method. Okay, set up a, set up a b to solve the coefficient. And then now this is what? This is ln. This is also ln, right? So the antiderivative we know. What do we need to do now? The first step we almost done. We find the antiderivative. Use the fundamental, right? ln absolute value x minus ln absolute value x plus 1 1 to t. Okay, one more step. Okay, this is the difference of the functions. Why we found the difference of the function, which is this ln. This t approach to infinity should be greater than 0, right? So I ignore this parenthesis, this absolute value. So it's this one minus ln. Here we can just use the parenthesis t plus 1, right? And then minus, which is minus 1 plus this is 0. 1 plus here is negative ln2 minus a negative ln2, which means plus ln2. Okay. The first step we done. We already dissolved the definite. Now the second step, going to find the limits. We have to go back to calculus 1, right? So calculus 1, you know. We look at this. This is infinity. This is infinity. You know. This is the indefinite type, right? This is infinity minus infinity. Everything could be possible. Okay, for this. So how to do? Merge them together. Okay, the basic method is merge them together. How to merge? Quotient, right? Remember the quotient rule. Quotient rule of logarithm. So if we merge them together, what it is? This is the limit t approach infinity. Okay, this over this, right? Which is ln parenthesis t over t plus 1. Okay, this limit, the constant number, of course, is itself, right? I put it here. Now, what do we need to do? Easy. The ln is a continuous function, so the limit can go inside, and then this is a rational, easy rational, and t approach infinity, infinity over infinity. But this is a easy one. Okay, you can divide it by t, divided by t. What do you get? Or if you remember the results, this is the limit 1. Okay, so I mean this is approach 1 definitely. Okay, so what it mean? It means this equals to ln at 1 plus ln at 2. Okay, I ignore the parentheses. What is ln1? ln1 is 0, so the answer now we get ln2. See, I will see this idea. 2 steps. The first step find the indefinite, definite integral. The second step take limits. Okay. Thank you. That's all.